Okay, hello everyone. Today we'll be looking at some grade 12 past papers. We'll be looking at the DBE November 2022 Physical Sciences paper 2 for grade 12. So that's the chemistry paper. This is the paper here. As we can see, it's a 3-hour paper for 150 marks. And I think there's around 10 questions. So budgeting your time, it should take about 20 minutes to go through each question roughly. Maybe a bit quicker so that you have some time to come back and double check your work. But yeah, okay. So for right now, we'll deal with question 1, the multiple choice section. There's 10 questions here. So getting straight into it. So question 1.1. Which one of the following terms describes hydrocarbons that contain only single bonds? So, from what we remember, if it only has single bonds, then it's a hydrocarbon. So we know all of these that are not carbons are hydrogens. Then this is an alkane. Now, another word for an alkane is saturated. That means that there's only single bonds, you can't do addition reactions. If you had double bonds, it is unsaturated. And what that basically means is you don't have the maximum number of, say, hydrogens that can exist in the molecule. So here we would only have 4 hydrogens compared to something like this, where we could add 6. Okay. So that's what they mean. So here the answer is, of course, saturated. Going on to 1.2. Which of the following combinations correctly indicates the strongest intermolecular forces found in ethanoic acid and methylpropanoate? So here we can maybe draw these molecules. So ethanoic acid. What does this look like? Well, it doesn't really matter exactly what it looks like. We know we have some hydrocarbon chain which corresponds to the ether part, which means I think 2 carbons, and then we have our carboxylic group. Okay, and what's important here is that we have some lone pairs on our carbonyl group, and we have this hydrogen, so there definitely can be hydrogen bonding. Okay. Now methylpropanoate. What can we expect to find in methylpropanoate? So it's an ester. And again, we don't really care about like the exact chains because the methyl part refers to the first part of the ester and the propyl part to the second part. The noate tells us it's an ester. So, okay, we have some carbon chain again, then our ester bond, and then some other carbon chain. And we don't really care about the carbon chains. But what's important here is that, sure, we have a carbonyl with some lone pairs, but there's no free hydrogen. There's no oxygen-hydrogen bond as there is in ethanoic acid. So there's no hydrogen bonding in esters, no hydrogen bonding. But there is a carbonyl, okay? So we do have some dipole interactions, but no hydrogen bonding, okay? So if we go back to our question, what does this mean for us? So ethanoic acid definitely has hydrogen bonding. Methylpropanoate, no hydrogen bonding. But not just London forces. It definitely has some dipole interaction. So our answer is D. Okay, moving on to 1.3. So we have bromine, and it's added to some liquid hydrocarbon, which they don't tell us what it is. Okay, and then they ask us what's going on. Okay, so they've given us a hint here. They've told us it's either hexane or hexene. Now, the thing is, if you have a saturated hydrocarbon, okay, I'll draw this stick way, something like that. That's hexane. And then you have bromine with all its lone pairs. It's got nowhere to attack this molecule. There's no way for it to attack. I can even put this in red. There's no way for it to attack. So this reaction is highly unlikely to happen. However, if you have hexene and it's on the second, the double bond is on the second carbon, all of a sudden bromine is going to have a partial positive charge and a partial negative charge, and all of a sudden we know the double bond is very nucleophilic. It has lots of electrons, so this is definitely going to be delta negative. All of a sudden we have somewhere to attack and a reaction can happen. So what does this tell us? This tells us that definitely hexane is out and we want to work with hexene. Now this reaction I've shown here across the double bond means we're probably going to get some haloalkane that looks like this, with bromine adding across the double bond, and that should give you a hint that it's an addition reaction. There's no oxygens, nitrogens, or other haloalkanes in order for it to be a substitution. There's nothing to substitute. It's just adding across the double bond. No hydrogens are lost. All the hydrogens that were in this molecule are still in this molecule. All we've done is added bromine across the double bond. So definitely it is an addition reaction. Okay, 1.4. Which one of the following statements is the correct definition for the rate of reaction? The time taken for the reaction to take place, the speed at which the reaction takes place, the rate of change in conc of the products or reactants, the rate of change in concentration of the products or reactants per unit time. All these definitions sound very similar. At this point, it would be useful if you would have memorized the textbook definition, because it's easy to get confused here. All of them sound the same. They're trying to catch us out. What I would definitely say is these two are definitely out. They're very simple. They don't talk about concentration. They don't talk about products or reactants. So our answer is most likely one of these two. Now, either choice is technically correct, but of course there's only one answer in the test. And you need to know your textbook definition. And in this case, the textbook definition is this one. You don't say per unit time. Now, that's just how it is. Because it's unnecessary to say per unit time, because the word rate already implies that. So this is the more correct textbook definition. You just have to know it. Okay. All right, 1.5. Consider the balanced equation for the reaction between magnesium powder and excess dilute HCl. Okay. The HCl is already in excess, yeah? Already in excess. Okay, good to know. So which one of the following will not increase the rate of this reaction? So increasing the temperature from our collision model means we're going to have magnesium atoms hitting H plus and Cl minus atoms or ions more often. So temperature will definitely increase our rate. Increasing the concentration of HCl just means there's more HCl per unit volume. So again, more collisions from our collision theory. Adding more magnesium powder is just the same as increasing its concentration. So for the same reasons as C, D is also going to increase our rate. So the only one that really doesn't do anything is A. And that's because when you increase the volume, you still have technically the same concentration of HCl, just more of it. So it doesn't really do anything. So yeah, A is not gonna increase our rate. Okay, 1.6. Two identical sealed jars contain gases. Okay, so all right, they give us some conditions. So basically we can see that this one is like the end of the reaction, and this one is like the beginning of the reaction. And then they let the reaction get to equilibrium, and it is reversible. So it's the same thing. So what you got to realize is that what's here and what's here are the same thing. So which one of the following statements is true at equilibrium? S will contain 1 mole of iodine. This is wrong, because in the beginning we had 1 mole. So basically, if jar S now has 1 mole, it's not at equilibrium. It's gone all the way to the beginning of the reaction. That's wrong. R will contain a larger amount of iodine than S. Again, wrong, because they're at equilibrium and it's the same reaction, so they'd contain the same amount. R and S will contain the same amount of hydrogen iodide. This is correct. So we know 1.6 is C. S will contain a larger amount of HI, so for the same reasons as A and B are wrong, this is also wrong. Okay, which one of the following salts when dissolved in water will not change the pH? So to do this question, first of all, it's very obvious the answer is D, because we have sodium chloride, which is table salt. And we know when we add salts to our food or anything we eat, it doesn't change the pH. It's a neutral salt. But just in case, let's say they didn't have a really obvious answer in the list of answers, how would you decide which is which? So what you got to realize is that Na plus essentially comes from something like sodium hydroxide, which is a strong base. And Cl minus comes from HCl, which is a strong acid. These conjugate acid bases, basically, they sort of cancel each other out. So if you have a compound that has ions that come from both a strong acid and a strong base, it's going to be neutral. But if you look at these other ones, all right, NH4 comes from ammonium, which is a weak base. COO over here comes from a carboxylic acid, which is, again, all organic acids are weak. And then CO3 comes from carbonic acid, which is also a weak acid. So you have these weak conjugates coupled with a strong base. And that's why these will not be neutral, and D will. But okay, moving on to 1.8. A dilute acid is titrated against a potassium hydroxide solution. At the equivalence point, the pH is 7. Which one of the following combinations correctly identifies the acid and the most suitable indicator for the titration? Okay. So the thing is, we have KOH, which is a strong base, and we have a pH of 7. So the only way to get this to happen is if we had a strong acid. That is the only way. So they try to trick us by saying dilute, but we must remember that dilute is not equal to weak. Okay, it just means a low concentration. So we know that our acid has to be a strong acid, and here there's a carboxylic acid is definitely out. Definitely one of these is the answer. Now the question is, which indicator do we choose? Here you just have to know the range of the indicators. Phenolphthalein is much better at lower pHs. So when your equivalence point is like maybe between 4 to 6. It technically could work as well, but the more correct answer would be bromothymol blue. And you just have to know this. You have to know the ranges of your indicators. Okay. All right, so for question 1.9, let's maybe define some of these things. Let me just make myself some space. Okay. So let's imagine we have some compound X reacting with some compound Y, and then all of a sudden we have X minus and Y plus. Okay. So these two could be ionic, they could form a single compound, they could just be ions existing in aqueous solution, so it could be XY, something like that. It could be a couple of things, but this is not what's important. What's important is that if we break up this reaction into a couple of half reactions, we have X going to X minus, so it gains an electron. And we have Y going to Y plus, so it loses an electron. Okay. And then we just have to remember our acronym, oil rig. So oxidation is loss. So if you're losing electrons, you're being oxidized. Reduction is gain. So if you're gaining electrons, you're being reduced. So if X is being reduced, that means Y is the reducing agent, because Y is having the effect on X to make it reduced. And if Y is being oxidized, that means X is the oxidizing agent, because X is having the effect on Y to make it oxidized. Okay, so this is just some useful information to help us answer this question. Okay, so which one of the following statements for an oxidizing agent is true? So as we just said, oxidizing agents are reduced, which means they gain electrons. So here the answer is straight up A. We don't even have to go through the others. But let's do it just for interest's sake. So it causes another species to be reduced. This is a reducing agent, okay? Okay. Its oxidation number does not change during a chemical reaction. Well, then it's not being reduced or oxidized, so nothing's happening, yeah? No electrochemical change. It's oxidation, so it's more like a spectator ion. This would be a spectator ion, you know? Its oxidation number increases during a chemical reaction. So if your oxidation number increases, like from plus or from 0 to like +1, that means you've lost electrons. That means you're an oxidizing. You're being oxidized, right? Which means you're the reducing agent as well. So again, these are the same thing. They're both reducing agents. This is a spectator ion, therefore A is the only oxidizing agent. Okay. Which one of the following metals will reduce cadmium, but will not reduce manganese? Okay. So let's just write down some half reactions here. So we have cadmium 2 plus 2 electrons going to cadmium solid. We have manganese 2 plus 2 electrons going to manganese solid. And we have some options here: zinc, silver, nickel, magnesium. Okay, so in order to answer this, we have to go to our redox potential, standard reduction potential table. And let's find cadmium. So where's cadmium? Cadmium is over here. Okay. And where's manganese? There's no manganese on this table. Let's try the other one. Okay, cadmium and manganese. So if we want to find something that will reduce cadmium but not manganese, that means it needs to exist. So it needs to be more negative than cadmium, but more positive than manganese to reduce this one, but not this one. And from our list of choices, we see that zinc is the only one that fits that criteria. So here, answer is zinc. Okay. And with that, we are done with the multiple choice section.